first, what we're trying to do is in this particular thing, when you go out of this meeting, what I want you to ask yourself question is, what have I learned in this, and what are the key things that you take away from this is, what is stream flow volume, okay? Why are we trying to predict the stream flow volume? And how I can use the government data to do some data analysis for your own interest. The end goal is not just money, for your own curious interest. If you can do some analysis and get some meaningful data, I think this course will be successful, okay? Those three things should be answered. So, first thing, what is this that you're seeing at? I mean, what am I looking at? This is all tax dollars at work. The government, USDA, there's a division in USDA called NRCS, okay, which is in this holiday state, a good part of the government which even paid their employees even during the shutdown thing, so they had some good funding in place. So they didn't keep their employees this thing, though some of their rural employees had their this thing all affected for this shutdown and all that. This, which is in the holiday street, they have this kind of system set up at various geographical locations in the West Coast and also in Colorado and someplace. So what you would see is, you would see something called snow pillow, a snow shelter, and a snow depth sensor. And what it does is, it actually calculates the snow water equivalent, okay? What it does is, it calculates various metrics, like how much the precipitation at the geolat location happened, and how much is the snow water equivalent metrics like that. And then they actually communicate to something called, they have their own channel, which is like the meteor showers. They transfer to that, and this meteor showers is something like a part of the atmosphere where it has this ionized kind of a state where it would communicate, and that would be received at various positions, and then around the clock, 24/7, 365 days, you would get the data. So they have their own communication systems in place, not using any of these public cellular networks and all that. So that's in place. Yeah, there's a whole bunch of patents and all that involved in that government, which they use this particular thing. So this system is in place, which actually gives us who consumes this data. Why are we interested? Like all the people, like the farmers or the people who have these recreation facilities, they want to, it's not something like, hey, weather is fine, let's go for the beach. No, it requires a bit of planning. Okay, this is the weather, like how much, is it going to be a drought season, or is it going to be sufficiently good? We have an enough water resources, then it requires a lot of planning. So that's when we have it. This is yes.
Maintained by whom? Some department under USDA?
Yeah, the NRCS USDA.gov. So if you go this particular thing, let's see if I can click, and yeah, should be able to get this link. There you go. This is the USDA Natural Resources Service, which is a federal government entity which actually does this important work. All right, so back to the slide. Okay, so now what we have is, now we have understood that this is the, okay, now let me go to the site and see how we can get the data. So I think I should be having that. Okay. Yeah. Okay, this is the end result what we want, but let's like USDA. Give me a minute. Okay, so you would want to actually make use of this thing called the report generator. Okay, and this is where you would actually select various parameters and how you would get the CSV file. What we want in the end of this is a data. So this is the thing which actually gives you a CSV file. So what it would actually, what are we looking at is select stations. And then what you would see here is a SNOTEL and all the other particular things, which we don't understand what we want. So let me explain two things which we would want to take away from this. One is known as the SNOTEL, and one is known as the Streamflow. Now, when I say Streamflow, what do you understand by that? What do you mean by that, Streamflow?
Continuous data.
No. That's not the Streamflow. See, there is a bunch of hydrologists in this particular thing. The people who are there, the software engineers are people who are enablers, but the key people in this department are all hydrologists, right? So what they do is, the river takes its flow from various geographical locations here and there and all that. At any geographical lat and long position, they have a way of measuring what is the volume, cubic density in that particular area. So that is the stream flow at what basin, at river basin, what is the value that you have at this altitude, this is the thing. So what happens, it's kind of seasonal, right? It's good.
So is it derived saturation?
Is that?
They're deriving saturation?
Yeah, they're deriving what is the volume of the river
so
water basin.
Synthetic, though. It's not really measured that. They're just estimating that.
No, they have a way of actually measuring that.
Okay.
There is a particular, they have installed a
Basin?
kind of a thing, which would actually flow in that, and they would actually see how much is the volume, acreage cubic feet that particular thing holds.
They measure it.
Yes.
And record it.
But the underground, I'm a farmer, so the water data is really important to me. So the ground's not uniform, and the water flows are going to go through it in various fluxy ways, right?
Yes, so it is an indicative at that position. Now, see, for example, your farmer, that particular thing will be coming at your position, might not be the true this thing. There might be a stream that would actually go in, and there are a lot of tributaries which would actually go. At that lat and long position, where they have measuring, this is what the acreage cubic feet index that they have.
And it's just a straight like scalar value, or is it a probability? Because I've drilled into a well and it's like, oh shit, there's no water here.
No. This is a river thing, right? River actually.
Oh, the river. Okay, got it. I'm so sorry.
Yeah.
I thought you meant ground flow.
No, not ground flow. Sorry, if I have confused you, I'm so sorry. Yeah, now we're good. See, questions are good. So it's a river thing which actually you measure that particular thing. Okay. Cool.
One quick question. Do they do this for every river or only selected? Every river?
Really
Yeah.
So they have this in important places on all rivers.
Yes, key positions. Yeah.
It affects how much you'll pay for your water, whether you're a farmer or whether you're a city.
Okay.
Big deal.
Big deal. Okay, so we know what we're predicting. So that is the response variable. Very important. We have to understand what's the stream flow. Okay, this is very important. So now we understood that one. And there's another thing which we're going to understand is the SNOTEL. So what is the SNOTEL? Is the thing which actually leads to that, what is driving that particular thing. For example, precipitation, snow. Let's say, oh, we had a very good snow. Oh, this time we had a very good precipitation. All this would yield to a lot of stream flow, which is like the river basins are pretty good, this particular thing. So that's the response variable, and this is something called the ones which actually is going to drive that variables.
So is snow actually part of precipitation? So will they measure precipitation as rainfall, or they will measure rainfall and snowfall at the same?
So it is the way they would do is they would have the precipitation index of that particular sensor, which would actually report that particular thing, and they also have the snow water, actual accumulated snow. It might be a thing wherein there would be a water way of handling things that sensor that would report. Okay, the transducers, there would be a combination of snow as well as the precipitation, but it depends on the sensors of what we have. Yeah.
And this is publicly available?
This is public.
That's awesome.
It's all, yeah. Nobody knows. Yeah.
What is SNOTEL? You said something. I missed it.
Snow telemetry is, I think, it's SNOTEL stands for.
Okay.
Yeah. Yep. So what we have is, okay, let's select the station which we would want, something like advanced search. Then let's OR, and then select the Deschutes. It says search, and then yeah, and then you would have all the things where you would have the places where you would want to actually have. So we can say close, and then let's see what we would want is, in this particular thing, I have used only one particular, the Deschutes are snow, this is the one, the station where which I have used. You can actually use whatever you would want, okay? So basically it gives you, this is where we would actually have the basins and also the SNOTEL. So here you would actually select the SNOTEL where you have the measuring thing. And also, yeah, let's see, 3 Creeks Meadow is what I have selected. So this is what I've used in my analysis site, but you can actually use it. So what I do is, I use an interactive map kind of a thing, which I'll also give you the website, the link, and open interactive map. So this is the thing, this basically uses the leaflets, which is actually open source software, which gives you a artist kind of a performance. So that you can actually see here, if you go to the snow depth, and then it opens, yeah, basically a map where you can actually select the basins and all that. So you can actually do a selection of this, like Streamflow adjusted volume, and then you can actually do a selection of that, selected stations. There's 885, like look at this particular thing, all the places where they have monitoring in place. For example, there's a whole bunch of things like, yeah, Oregon, California, yeah. So you have all this, so you can actually do the selection of that. And then, yeah, states. So this is something really, I mean, just for your own understanding, you can do this particular, in a minute. So yeah, you can select that particular thing and the county, and then make sure that this map actually maps to the ones which you wanted. Yeah. And then, yep. And then here you can actually, yeah, what the heck. There you go. It actually tells you of this particular basin of what we are trying to see here, okay? So it's going to show you how much is the stream flow. Is it coming here? Yeah, export CSV. You can actually export that particular thing for the 1 month. And then you can, this is all publicly available data. Like you can actually see the county of where and all that, and the elevation to this thing, and then what is the value of we have. So in my example of what we're going to see is, I have actually custom queried this particular thing and then have used it. So let me show what we have. Yeah, why is this coming like that? Should we move it somewhere else? Yeah. Let me take this out. Oh, there you go. I think I've already copied that. Yeah. So, yeah. So basically you would actually get this, if you query that particular thing, and then you would get what the values you would want. So what I've done is for the next 10 years, starting from 2007 to till now, I think for every month on an average, what is the, I have actually basically taken the response variable and the exogenous variable, which I would want. For example, in this particular case, you would see for the Deschutes River below Snow Creek is something like that. The stream flow volume, okay, I have used it. And also I've used something like 3 Creeks Meadows precipitation and 3 Creeks Meadows snow water equivalent. So that I have captured using this. So that's the bulk of this particular.
So is the snowfall your exogenous variable, and then the stream flow your response variable?
Yes, yes, yeah, perfect. So both the precipitation and the snow water equivalent are the exogenous variable, and then the response variable is that one. Yep. And so moving on to this, yeah, let's actually go through this model of what we have. Unfortunately, there was some issue about this Oracle licensing, which they made it this thing. So I will get this working in the next part series, but I can actually explain what I have done in this particular whole analysis.
What's Zeppelin?
Zeppelin is a interpreter, like how you would have Jupyter for Python.
So
It's like for the Scala, what I've used is, yeah, I've used Scala and Apache Spark for getting this thing into work. Yeah, so pardon me, there were some issues which I couldn't address for this particular meeting, but I'll be able to do that. But what this is been implemented in USDA. So what I have done here is, I've taken, let me explain this.
Could you please,
yeah.
could you please do Control Plus so we can see better code?
Control?
Control Plus.
Control Plus.
One more time. That's very good.
Yeah.
Thank you.
All righty. All right. So let me explain what exactly, before we dive into that code. Yeah. Let's go to the presentation. Okay, so first of all, there is something like, yeah, we understood what the Streamflow volume is, and I have to explain what the density is all about. The density of the powdery snow, what you would get, right, that has a very low density, meaning like, okay, if somebody puts in a snow, which is all the powdery, the good snow, it's not naturally, it has less water density. So when you convert into water, there's hardly anything, but the ones which are very thick are obviously having more higher density. That means to say, yeah, they are very good for the nature, meaning they result in more water for us. So that's some terminology that we would use it. And then this is what the actual data would look like. You would have any time series data, you would have always one column having, this is actually monthly data. So you would have a monthly average of what the observed value, the thing is in acreage per cubic feet. That's the stream volume, which is the response variable. The Three Creeks Meadow is the place from where we are actually taking the precipitation accumulation, which is in inches, and also the snow water equivalent, which is abbreviated as SWE. So these are the things that we would actually take in.
And so the current is already the average of the month.
Average of the
Do
month.
you know how many data points they collect in that month?
We have it on a daily basis kind of a thing.
Oh,
Every
okay.
daily we would actually
They
have,
just give you the average.
which would give an average value of that particular thing. So,
What are your 5 W's?
oh yeah, the 5 Ws. Yeah, so you should know when you look at the data, you should ask like, what are you talking about? The what, the who, the when, where, and why. Yeah. So I
We
think,
don't have to sell the station.
yeah. So have this in your things, like when you look at this particular thing, yeah, the what is, what are you talking about is the streamflow volume, where it was collected in Deschutes River, and then why are we doing this? So that it can help in our planning, the irrigation planning. So that's the thing. Okay, let's look at the actual thing that what we've done, the work. Yep. So I'm sorry about the exceptions. I'll be able to explain the next time better, but I can actually yeah. So what we do is in this particular, when you have this particular data, Spark is basically, what is Apache Spark? Apache Spark happened in 2014. Basically, there was a bunch of engineers who were like, I think Jupyter happened around 2012 or 2013, and then there was this consensus of people having the skills of Scala, which is gaining prominence as a functional language. So they wanted a model which can actually have this as a, DAG, directed acyclic graphs. Yep. So
What is it?
DAG, DAG, directed acyclic graphs. So basically, what you
Spark's the database.
was that?
Spark's the database, right?
No, it doesn't. So,
Computational engine.
yeah, it's a computational engine kind of a thing. So what happened is they created a model which, so which actually does it, for example, the lowest hanging fruit first and then comes the top kind of a thing. So they created a model called Apache Mesos, and then they said, and they wanted a thing to make this work in a very robust way. And then as a result of Apache Meso's framework, then this Apache Spark was actually brought in. So Spark was, there's a gentleman called Matthijs Zaharia. He's the prime guy who brought this particular thing around 2013 or 2014, which was actually in the AMP labs in UC Berkeley. It was actually, there was another, like how we have NumPy in libraries in Python, they have this David Hall in Berkeley. He started using Breeze libraries, which is again linear algebra. Linear algebra is pretty important in order to do anything. For example, doing an identity matrix, or you want to do any inversion, pseudo inverse kind of matrices and all that. So that library was available. So that's when they said, oh yeah, Scala ecosystem is there. So now we have a framework, Apache Spark. So let's begin. So, and then also they had some support just to attract the Java developers who said that, okay, we're going to give you, because it was JVM anyway.
So Spark's like a runtime library collection for Scala? I'm confused about what Spark actually is.
Apache Spark is the framework where you can actually run all the data science algorithms.
Okay.
Yeah.
So Apache Spark is different from Spark.
Same thing.
What is? Yeah, I thought yeah, it's the same thing. Yeah.
And also, how is it different than Hadoop?
Yeah, Hadoop was not an in-memory thing; it was a file-based kind of a thing.
Yeah.
So the seek time to get that particular thing was very laborious. It was very painstakingly huge, and the time was like not good for the multi-pipelines. Like if you want to do a genomic research and all that, you have to be like quick on all that particular thing. So all this DNA sequencing and all that. And Hadoop was, Hadoop was not that good enough. So they wanted in-memory thing to
Computation.
Yeah. So they said, oh, distributed computing is taking place. Memory is kind of cheap. Let's do in-memory thing. So that's how everything worked yeah. So I'll get this thing working in the second session, but I can actually explain what this was all working. But thanks to Oracle making it the licensed version, and I was interested in the open source one, the Open JDK. I think the libraries had some tweaking to do.
So where were you using Oracle in all this? Okay, you
JDK.
store data?
JDK.
So store your results?
No, Oracle is just the JDK.
Oh, JDK.
Yeah.
Java.
Yeah. So now let me briefly explain what I'm trying to do in this whole thing. So you read, this is, I think, even if you're conversant with the pandas library in Python, you would basically take a CSV and you would read and get a data frame. I think that's what we would do in Python, right? So that's equivalent of here is this particular thing. I'm trying to do this. I read the format, I'm telling it's CSV, and I'm telling you there are headers in this, and then infer the schema all by yourself. And I just give you a CSV file, which is basically, if you do a VI on this particular thing, it's just this particular thing. Yeah, date, there are only 3 things. I can actually show you much better in this way. There you go. This is all it takes. So there's about 3 variables and then along with the date. So totally 4 columns. So that's all you have it here. And where I go? Yeah, there you go. Zeppelin. Zeppelin is a symbol of that, that balloon which got exploded. There was this Apache Zeppelin. Yeah. So that's the symbol of that. Yeah.
That's a funny brand.
Yeah. So that's the data frame thing. And then what I do here is, the next demo I should be able to show everything. But yeah, next I basically define something called a user-defined functions. What are user-defined functions? It's like the thing what you would actually have it in a Spark's data frame actually gives you ability. If you are coming from an SQL background, you would be conversant with, hey, what is the average of that column? What would be this thing? You would actually say select average of that column from blah, blah, blah. So that's something which is already in place, that kind of lingo. So they said, okay, people are coming from this ETL background and all that. So let's give this thing called user-defined function. So you would actually write that in a Scala of how would you want to do this. So for example, what this thing does is just trying to do, take a string variable and making it into a zone day time, something like a different thing. So it's pretty handy to call your own functions, the user-defined functions, and basically transform from one class to the another class kind of stuff.
So don't they have a library and stuff for that? Or
Yeah, there's a library.
So why are you doing it on your end? You just call them their functions for it.
Some things are out of the box. Like for example, you would go to a McDonald's and say you would want this particular thing, but if you want to go to a classy restaurant and say, hey, I don't want that, make me this.
God, you want a particular version.
Yeah, so we don't want just from the menu, but we want classy stuff like that.
So the question is, this code belong to which programming language? Scala?
Scala.
Oh, sorry, I try to understand. So Scala is a type of language.
Language.
Yes,
It's a functional language.
it's a functional programming language. Yeah.
It's like, its objective is to kind of oversee Java, right? It's like,
It's that Martin Odersky from, I think from Germany. He's a German guy. Yeah, Scala. He wanted to
address the Java problems, isn't it?
No, he had this inkling towards the Erlang's way of actor-related concurrency thing. You know, this Erlang's concurrency way of doing that actor-driven thing, wherein nobody shares a state, and then I take care of this particular thing. I mean, thread programming is serious business, and it is very, you pull your hair out. Yeah. So what he said was, okay, I'm going to go way of doing the Akka way or the Erlang way of doing things. So which is basically an actor-based system is what they call it. An actor-based systems already have, like, an actor can actually change its behavior and also can create multiple actors. So then he said, okay, I'll make this Scala programming language, which actually has a lot of implicits. It has a lot of monads. It has a lot of, the programming language, if you actually see, it has a lot of immutability in place. So it's good for us.
So
I think.
you would choose it for a heavily multi-threaded app?
Yes, yeah. So it is suited for that particular thing. I think among functional programming language, this is the taking place. But yeah, in a general programming language, I think Node.js or Python is scoring much higher than Java.
So for your problem domain, why did you settle on a functional programming language versus like an object language or a procedural language?
So no. The thing is that the system in USDA was Java heavy. So there was like JDK, all the libraries were already available. And if you want to get some system, this thing, it was all Java based system. So it was, JVM was already in place in the USDA systems. So I had to make a library which is in compliance with that particular thing and also data science friendly. So I thought, okay, the best thing that I can do at that point of time was Scala.
No, so when you're loading your data frame, your JS calls, they're not JavaScript calls, they're Java calls. Okay, okay, got it. Thank you.
No, they're all Scala calls.
So can you go back to when you were loading the data frame because you called JS stuff?
There you go.
Oh,
yes.
So what's the call to Java utility?
Oh, that is internally. So that whatever that you was calling this thing, Java util concurrent. Yeah, it makes use of that particular JVM from the server side. But yes,
Scala sits on top of JVM.
Yeah.
It utilizes JVM.
So
built on Java.
Yeah.
No, but
So it's like Python, you have all.
So that's a stack you got to decide.
What I have heard is that Scala is more efficient and faster compared to Python. That's what I heard when I took some course last year.
I think Python is much faster, but the scalability aspect, I think, is what I thought. But now even I think IPython has, I mean, Jupyter has a way of.
Excuse me, that was vice versa. What you say is vice versa. Python is faster than this is.
Python is faster, that's what I've heard, but it can't scale it is what I've said. I've heard is what I've heard.
Yeah.
This was a year ago, so
Yeah, well, the other way.
So you say Python cannot scale very well, because Scala can deal with large amount of data.
Yes. Yeah.
But how much data is huge amount of data? Like we always talk about big data stuff.
120 GB is what I have handled.
The memory.
120 GB data is what I have handled to the maximum when I was a data scientist. But people have handled, I don't know, the various roles people have done much bigger. Yeah.
No, but Python can handle big data too. Yeah.
You know what the problem is? Everything works here, okay? When you put it on cloud, nothing works, right? So that's what you'll experience. And then you have to think like a Batman as well as a Robin, right? You have to think like, oh, data science is working. How many parallels you have to do? How many, the configuration parameter is a tricky business. So everything works here. Small data and everything works. But yeah. So
No,
those
but
that's
the answer to your question.
Yeah.
He has to use a Scala because the client using the library from Java.
Java.
Right.
Now, you have to be careful about that because the question is how many jobs we have available using a Scala for data science now?
Sure.
Practically nothing.
Right.
So to be very careful. It doesn't mean that you have to go tomorrow morning to learn Scala to do data science because it's no job for you.
Sure. Right.
It's just specific for this client, you know.
It's a
So
very
don't
different-
think in this way, you know, that because
Right.
right.
It said alternate stack.
Yes, that is correct. He went there, he used it, he has to use Scala for that.
yes.
But in real life, we don't do that. We
No,
use
it's like
Okay, okay.
It's got, oh, that's good.
yeah.
So-
No, yeah, just in case.
And then what we do is we actually define new columns with this with column, like what we would. Why is it? Yeah, can't see properly. Is it command minus or something?
Yeah.
No. Yeah. So let me explain. Yeah. So what I do is, okay. Before we look into the code, let me explain to you like a layman thing, and then we can look into this code. Okay. So what I do is, I take this particular. Now we have a Streamflow volume. You have the precipitation and the snow water equivalent, right? So what I do is I basically take the autocorrelation, see how much is the linear trend towards that particular thing. So I use this thing called correlation. That's what I do here. Where is it? Sorry, I went very far. Yeah, so I do the, just give me a minute. All right, there you go. Perfect. There you go. So I basically take the correlation of that particular thing, and then with the Streamflow, how much is how correlated? You know what the correlation is, right? It's the Kendall row, or you have this particular thing which actually takes the how correlated it is. It's a pretty a term which actually measures how much linear trend it is. So I take that particular thing and then I dust it on a bell graph with the standard scalar. What you're trying to see is basically what you're trying to do is you would want to actually take a bell graph with zero mean and univariance, one variance, and then just sprinkle that particular data on that and see how that particular sets, and take that data and then make another variable out of that called a C bulk, which is like basically one variable out of these two variables. And I also do something called a deseasonalizing that particular data. What do you mean by deseasonalizing data? Meaning, for example, if you want to actually see the trends, let's say if you're running something like a water park kind of a thing, in summers you have the business coming like this, and in the winter it will be low. So there, there will be some seasonality. It's not like a uniform thing. So when we are trying to mimic the particular trends, we actually take the overall mean and also minus from that whatever that particular month is. So we don't actually have a very peaky kind of a data kind of a thing. So we take care of the deseasonal aspect. And then what we do is, with now the data is being ready, where we have something like, we create another variable called C bulk, which is basically, Z is always been a short form notation for a normalized one. Okay. So
what's the difference between deseasonalization and normalization?
Normalization is a Z thing, okay? So where we would actually want to say, okay, now we know for sure, okay, you can be of your own type of whatever random distribution that you have, but in your, if I were to actually assess you in a normalized way, how would you look like? Is when you would actually sprinkle all the dots on a one variance, zero mean curve. So that's the Z thing. That's the normalized one. And then you would actually get a C bulk variable. And then what I would do is I would actually, now that everything is ready, now we do the time series calculation. So the whole thing about time series calculation, what we do in this time, what is white noise. It's all about white noise. Okay, what is white noise? If you are from electronics background, electronics was pretty big in Oregon. So I think so if you take a delta signal, delta of t at 0, you'll get just a single spike, right? Delta of 0. And the whole of electronics and communications, what we do is we study how to convert a signal in time domain to frequency domain. I think we study that for about 3 to 4 semesters. So that's all we do, okay? Take a signal in time domain, convert into frequency.
Just Fourier transform?
Fourier transform, perfect. That's the periodicity of that Fourier transform, but that's all it is. So if you take that delta of t, which is like if you take the time is equal to 0 and take one simple amplitude of 1 and then put it in the frequency domain, you will have a signal which is at all frequencies, you will have a complete amplitude, and that's called white noise, okay? So now, white noise, yes. So that is white noise, okay? So now what we're trying to do is, white noise is easily be removed. When you actually do this autocorrelation, when you actually regress with time, you can actually remove that particular thing. So now what we're trying in this flow, this ARIMAX is what we're trying to do is, trying to see what is the degrees at which you have significant reduction of these errors. So there is something called white noise, and there is non-stationary noise as well. So how do we address it? There are 3 parameters which we want to identify, which is, first of all, we look at the plot of autocorrelation function, okay? So this is called as ACF plot. I'll get this showing everything, all this in the next session. But what we do in the autocorrelation function is, what is autocorrelation? Taking the same signal, delayed, and then you're trying to see the correlation of these two. Is nothing but an autocorrelation function. So when you do that, you get to see how much is the, what is the nature of the plot? Is it kind of a, I have a book which I got from Amazon, which is, yeah, I think, oh, sorry for that, yeah. So this is the book which I got for just $3 because this professor released a new book, and what I needed was just enough in this previous version. So yeah, it worked for me. So that's what I used in that. So that we used to, we use this particular plot to identify at what point there are 2 measuring variables. Like when you're actually doing this test, what are you looking at? You're trying to minimize something called Akaike information criteria, which is in short form AIC. And there's something called Schwarz information criteria. So these 2 variables which you would want to see where it leads to the minimal. So we'll be keep on plotting and identifying what the values we get. This is called PACF, which is partial autocorrelation. So those 2 things are very important. And then we actually see how the coefficients are, where the approximate AC is the double value, which we get the minimal value. And then once we get that particular thing, we try to see, okay, for the values which we have, when we have the minimal values, we try to plot what was, like, let's say we take 6 months less than what we have, and then try to see, okay, from these gleaned data from the last 10 years, can you tell me for the next 6 months what your curve looks like? Okay, now we will draw the curve. Now we will get the data from the actual environment and see what the curve looks like. Is it a close resemblance of that? Just by looking at that, is it closely mimicking that? If there is a various deviation, then your model fails. But if it's closely mimicking, then you're good to do. So this is what was the exercise which we did, because my professor in USDA, he was a data scientist. I think, yeah, it's funny. His view of data scientist was like, yeah, he was a very, very good fellow, very humble. Yeah, and yeah, nice gentleman. So that person, he wanted me to work on starting with time series and then go with the neural and all that, because he could understand what was, how the time series behaved, and then he could understand from one model to other model and that model. So his name was, yeah, David, I forgot his last name yet. So his name is David. So he suggested us to start with the time series flow and then go with the neural model. So that's how we got this particular thing. It closely mimicked. What is the downfall of this? Yeah, see, as I said, the P. The P value is nothing but the one which you would actually use it for the auto regression, which we would get it from the partial autocorrelation function. The Q is what we would get for the moving average. The D is if it's non-stationarity, we do that integrated kind of thing. So that is ARIMA. And then X is the exogenous variable, what Daniel pointed out. It will be the bulk, the C bulk thing which we used. So this is nothing but the combination of the normalized precipitation plus the normalized snow water equivalent, combine that, and then we do this particular thing. It gave a pretty good thing. This model is really give very good results. I can actually show in the next session of how it closely mimics the particular curve. But this is the model for everything. I had challenges too. Whenever there was a forest fire, this model did not work good because I tried to do, if this model is like this, the actual curve was something like that. I had difficulties. So at that moment, whenever there was forest fire, I had to take data from not the longitudinal region from that particular region, but also because whenever there's forest fire, there was nothing to hold this particular thing and the water would rush in certain things. So it would create a chaos for predicting and all this particular thing. So it's a very big challenge, and they use 3-4 NOAA models kind of a thing, which is a combination of neural and also some their patented NOA model, which is a complicated, how to put that. They have their own SAS code for that software. There is also a language called SAS. It's a old statistical language, which was it's in.
I've heard of that in like 20 years. Yeah, you're right.
It's based out of North Carolina. Yeah, I think.
Yeah.
I'm done.
All right. Thank you.